So the first big question is, what exactly is an electric field? Well, an electric field is best described in words at least as a region of space in which a charge feels a force. So if you've got a charged particle and you put it somewhere, well, if it kind of feels pulled in some direction or another, then there's an electric field there. And so it's worth just remembering that gravitational fields are similar, only they are regions of space where mass experiences a force. But gravitational fields come in a later course. So there's an equation describing the strength of an electric field, and that equation is E equals F over Q. And this is a really, really fundamental equation for electric fields. So let's just kind of really make sure we know what's going on here. So capital E is what's known as the electric field strength. And we can see that it kind of ties up with the definition of electric field, a region of space in which a charge feels a force, because we're defining electrical field strength as the force per unit charge. So the force per coulomb. So that gives us a way to compare different points in an electric field or different points in different electric fields. Let's just take a look at the units. Well, newtons is clearly for force, coulombs is for charge. So that means that electrical field strength is going to be measured in newtons per coulomb. So let's highlight that because that's a really crucial equation, one that is given, but really I recommend to know that one inside out. Okay, so, well, how might we describe a field? Well, usually field lines are used in order to draw an electric field. Now, of course, these are just a kind of an intuitive model of what an electric field might look like. I mean, I'll draw a few field lines. Here we are. Well, when you see field lines, you'll just see lines with arrows, basically. If we go back to the equation, force is a vector, charge is just a scalar, but so field strength must also be a vector because it's just a vector divided by a number. So this is a vector quantity. So that gives you a clue as to what the arrows, when we use field lines, what the arrows represent. The other thing you might notice there is that in my particular drawing, the field lines kind of are swooping away from each other. Well, that also has some kind of significance, and there are really two things to bear in mind about field lines. The first thing is that the closer the lines are together, the stronger the field is. Yeah, the closer the lines, the stronger the field. Now, there's no kind of scale or anything like that. It's just an arbitrary relative scale. So I could look here at this particular diagram and I could say, oh, well, just in that orange region, the lines are quite close, and then they kind of spread out more. So the field is going to be stronger over on the left-hand side. Yes, so there's going to be a bigger force per coulomb because the lines are close together, and it's going to be weaker over on the right-hand side because the lines are further apart. So that's kind of good to bear in mind because it's useful when we come to specific types of field that we need to know about. There's another thing which is, and I've already hinted at, the arrows show the direction of the force basically, but we need a little bit more precision about that. Well, the arrows show the direction specifically in which a small positive test charge would accelerate if at that point in the field. Okay, well, there's not an arrow at every point in the field, but you know what I mean. If I put a small positive test charge there, it would follow the field line. If I had a small positive test charge where there is no field line, well, you have to sort of figure out what the field direction is there, and it's obviously kind of in the direction of the two field lines above and below. So that's very, very important, and it's important to remember that it's the direction that a positive charge would move rather than a negative charge. A negative charge, you might guess, would therefore move in the opposite direction. And that's quite important later on when we have particle physics, with things like electrons and protons and all the rest. You have to think about the charge to decide what it's going to do. We also need to consider what's meant by this small, well, we know what small means, but test charge. You know, what does it mean, a small positive test charge? Well, let's take the phrase as a whole. Well, the reason that's in that description of a field line there is that if we put a charge which was positive but too big, well, it would have its own field, electric field. It would be generating its own electric field, and it would mess up the field line that we're kind of looking at. So it has to be so small that it wouldn't actually have a negligible effect on the field around it. So that's why we say a small positive test charge, like a little charge which isn't going to actually affect the field. Great, well, those are the preliminaries. And look, let's just have a quick go at using that equation in an example. So here's an example, and let's see what it says. Well, it says, okay, what would be the acceleration of a proton placed at a point in an electric field where the field strength is 250 newtons per coulomb? Well, we can hopefully do that fairly straightforwardly, just using the equation that we've learned. Well, we can find the force by rearranging the equation. F equals EQ, and they tell us E is 250 newtons per coulomb. Well, the charge on a proton is what we might call E, which we know what E is, so it's 250 times 1.6 times 10 to the minus 19 coulombs. That's the force. Now, we haven't got a picture of this particular field, but we know the direction would be in the direction of the field lines that it experienced that force. Then to find the acceleration, we just use F equals ma, so we do F over m, and so that's going to give us our final answer. So we're going to end up with 250 times 1.6 times 10 to the minus 19 divided by the mass of the proton, 1.67 times 10 to the minus 27. And if we evaluate that, hopefully you agree that we get a rather huge acceleration, 2.4 times 10 to the plus 10 meters per second squared. Well, that's a massive acceleration, but it really ought to be, because a proton is very, very tiny. So it's going to whiz away real quick and get accelerated off pretty quick in that direction. So those are just the first ideas. So just have a go at the one or two questions before moving on and looking at different types of field in somewhat more depth.